the discovery of gravity stands as a pivotal moment in human understanding, forever altering our grasp of the universe. It was a revelation that not only reshaped the landscape of physics, but also influenced the very fabric of our existence. As we embark on this journey through the ages, we find ourselves poised on the precipice of a profound truth. The universe's most elusive secret is also its most binding force. In the ancient world, where the whispering winds carried the secrets of the cosmos, humanity's understanding of the universe was shrouded in mystery. The earliest civilizations, nestled between the Tigris and Euphrates rivers in the Fertile Crescent of Mesopotamia, gazed up at the star-studded sky, pondering the workings of the celestial ballet. It was here, in the cradle of civilization, that the foundations for our modern comprehension of gravity were laid, though the concept itself would remain elusive for millennia. The ancient Greeks, with their insatiable curiosity and passion for knowledge, made significant strides in understanding the natural world. Philosophers such as Thales of Miletus, who lived in the 6th century BCE, began to speculate about the fundamental nature of reality. Thales, often credited as one of the first Western philosophers, proposed that water was the basic substance from which all matter was derived. Though his theory may seem simplistic by modern standards, it marked a crucial shift towards a more rational understanding of the world. As Greek philosophy continued to evolve, other thinkers, such as Aristotle, made notable contributions to the discussion. In his work, Physica, Aristotle explored the concept of natural motion, suggesting that objects tend towards their natural place. He proposed that heavy objects have a natural tendency to move towards the center of the universe, while lighter objects tend to rise. Though Aristotle's ideas about gravity were limited and often misguided, his work laid the groundwork for future scholars to build upon. The Greek concept of horos, or boundary, also played a significant role in the development of gravitational theory. The idea that objects have a natural tendency to move towards their appointed place, or horos, hinted at a deeper understanding of the forces governing the universe. This notion would later influence the work of medieval scholars who would strive to reconcile Aristotelian philosophy with the emerging principles of physics. In the ancient Greek city of Alexandria, a hub of intellectual and cultural exchange, scholars such as Eratosthenes and Archimedes made groundbreaking contributions to mathematics, astronomy, and engineering. Their work, particularly in the fields of geometry and trigonometry, would eventually provide the tools necessary for later scientists to quantify and describe the force of gravity. As the intellectual fervor of Alexandria continued to simmer, the works of Eratosthenes and Archimedes found their way into the hands of medieval scholars who sought to reconcile the principles of Aristotelian philosophy with the emerging tenets of physics. One such scholar, the Persian polymath Ibn Sina, also known as Avicenna, made significant contributions to the understanding of motion and gravity in the 11th century. In his seminal work, The Book of Healing, Avicenna proposed that objects tend towards their natural place due to an inherent force, which he termed male. This concept, though not entirely accurate by modern standards, marked a crucial step towards the development of a more nuanced understanding of gravity. Meanwhile, in Europe, the works of Aristotle and other ancient Greeks were being rediscovered and translated into Latin, sparking a renewed interest in classical learning. The University of Oxford, founded in the 12th century, became a hub for intellectual inquiry, attracting scholars such as Robert Grosseteste, who wrote extensively on the nature of light, color, and motion. Though Grosseteste's work was not directly focused on gravity, his emphasis on the importance of experimentation and observation laid the groundwork for future scientists to explore the natural world with greater rigor. In the 14th century, the Oxford calculator Thomas Bradwardine made notable contributions to the study of motion, proposing that the velocity of an object is directly proportional to the force applied to it. This idea, though still rooted in Aristotelian thought, marked a significant departure from the prevailing views of the time. Bradwardine's work, in turn, influenced the thinking of other scholars, such as Jean Buridan, who proposed the concept of impetus, suggesting that an object's motion is the result of an internal force imparted to it by an external agent. As the concept of impetus gained traction, It laid the groundwork for the work of Galileo Galilei, a 16th-century Italian physicist who would revolutionize our understanding of motion and gravity. In his seminal work, Dialogue concerning the two chief world systems, Galileo challenged the prevailing Aristotelian views on motion, proposing that objects in motion tend to maintain their velocity unless acted upon by an external force. This concept, known as inertia, marked a significant departure from the traditional understanding of natural motion and paved the way for a more nuanced comprehension of gravity. Galileo's experiments with rolling balls down inclined planes and his observations of pendulums allowed him to quantify the relationship between distance, time, and velocity, providing a foundation for the development of modern kinematics. His work also sparked a renewed interest in the study of motion, attracting the attention of other prominent scholars, such as Johannes Kepler, who was working on a new understanding of planetary motion. Kepler's discovery of the three laws of planetary motion, which describe the elliptical orbits of planets around the Sun, provided a crucial piece of the puzzle for understanding gravity. His third law, in particular, which related the orbital periods of planets to their distances from the Sun, hinted at an underlying force governing the motion of celestial bodies. This work would later influence Sir Isaac Newton, who would build upon Kepler's discoveries and Galileo's principles of motion to develop a comprehensive theory of gravity. In the mid-17th century, the English scientist Robert Hooke was experimenting with springs and pendulums, attempting to understand the nature of force and motion. His work on the behavior of springs led him to propose the concept of a universal force that acts between objects, which he described as an attraction or pull. This idea, though still rudimentary, foreshadowed the development of Newton's law of universal gravitation. Hooke's correspondence with Newton, who was then a young scholar at Cambridge University, sparked a lively exchange of ideas on the nature of motion and gravity. Newton, inspired by Kepler's laws and Galileo's principles, began to develop his own theory of gravity, which would eventually become the cornerstone of modern physics. As Newton delved deeper into his research, he became increasingly fascinated with the behavior of comets and the orbits of planets, recognizing that a universal force must be at play to govern these phenomena. Newton's work on optics and mathematics, particularly his development of calculus, provided him with the tools necessary to quantify and describe the force of gravity. His most famous experiment, involving the falling apple, has become an iconic representation of the moment when the concept of gravity clicked into place. However, it was not a single eureka moment that led Newton to his theory of gravity. Rather, it was the culmination of years of intense study, experimentation, and correspondence with other prominent scholars of his time. As Newton's understanding of gravity deepened, he began to see the universe as a vast, interconnected web of forces, with every object exerting an influence on every other. His work on calculus, particularly his development of the method of fluxions, allowed him to model and analyze complex systems such as the motion of planets and comets. Newton's manuscript, De Motu, written in 1684, laid out his initial thoughts on gravity, including his concept of a universal force that acts between objects. Newton's correspondence with Edmund Halley, a fellow English scientist and astronomer, played a significant role in shaping his ideas on gravity. Halley, who had been studying the orbits of comets, recognized the importance of Newton's work and encouraged him to publish his findings. In 1687, Newton's masterpiece, Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, was finally published, thanks in part to Halley's persistence and financial support. The Principia, as it came to be known, presented Newton's law of universal gravitation, which states that every point mass attracts every other point mass by a force acting along the line intersecting both points. The law, often expressed as F equals G times m1 times m2, divided by r squared, where F is the gravitational force, G is the gravitational constant, m1 and m2 are the masses of the objects, and r is the distance between them, provided a fundamental explanation for the motion of celestial bodies. Newton's work on gravity also had a profound impact on the study of optics. His experiments with prisms and lenses led to a deeper understanding of the nature of light and its behavior. In his book Optics, published in 1704, Newton presented his findings on the composition of white light and the properties of colors, further solidifying his reputation as a leading scientist of his time. As news of Newton's work spread throughout Europe, it sparked a lively debate among scientists and philosophers. The French scientist and philosopher, Pierre-Simon Laplace, was deeply influenced by Newton's ideas and went on to develop his own theories on celestial mechanics. Laplace's work, particularly his Celestial Mechanics treatise, published in 1799 to 1825, built upon Newton's foundation and provided a more detailed understanding of the solar system. The study of gravity also attracted the attention of other prominent scientists, such as Joseph Louis Lagrange, who made significant contributions to the field of celestial mechanics. Lagrange's work on the stability of planetary orbits and the behavior of comets helped to further refine our understanding of the universe and the forces that shape it. In the late 18th century, the English scientist Henry Cavendish conducted a series of experiments to measure the density of the Earth, which ultimately led to a more precise calculation of the gravitational constant. Cavendish's work, published in 1798, provided a fundamental constant that would be used by scientists for centuries to come, allowing them to make more accurate predictions about the behavior of celestial bodies and the strength of gravitational forces. As the 19th century unfolded, the study of gravity continued to advance, with scientists building upon the foundations laid by Newton, Laplace, and Lagrange. One notable figure was Carl Friedrich Gauss, a German mathematician who made significant contributions to the field of celestial mechanics. In 1809, Gauss published his treatise, Theoria Modus Corporum Coelestium, which presented a comprehensive theory of planetary motion and provided a more precise method for calculating orbital trajectories. Gauss's work had a profound impact on the field of astronomy, enabling scientists to make more accurate predictions about the behavior of celestial bodies. His methods were soon applied to the study of comets, asteroids, and other small bodies in the solar system. The French astronomer Félix Tisserand, for example, used Gauss's techniques to calculate the orbits of several comets, including the famous comet Halley. Meanwhile, the development of new technologies, such as the telegraph and the railways, facilitated communication and collaboration among scientists across Europe. The Royal Astronomical Society, founded in 1820, played a significant role in promoting the study of astronomy and gravity, providing a platform for scientists to share their research and ideas. The Society's journal, the monthly notices of the Royal Astronomical Society, became a leading publication for astronomical research, featuring articles by prominent scientists such as John Herschel and George Airy. In the mid-19th century, the study of gravity took a significant leap forward with the work of William Thomson, Lord Kelvin, and Peter Guthrie Tait. Their treatise on Natural Philosophy, published in 1867, presented a comprehensive overview of physics, including a detailed discussion of gravity and its role in the natural world. The book became a classic in the field, influencing generations of scientists and shaping the development of modern physics. As the 19th century drew to a close, the study of gravity continued to evolve, with scientists exploring new areas of research such as the behavior of gravity in extreme environments, like high-speed rotations or intense gravitational fields. The work of scientists like Hendrik Lorentz and Henri Poincaré laid the foundation for the development of modern theories of gravity, including Albert Einstein's groundbreaking theory of general relativity. In the early 20th century, Einstein's theory revolutionized our understanding of gravity, introducing concepts like space-time curvature and gravitational waves. The theory was soon tested and confirmed by a series of experiments and observations, including the famous solar eclipse expedition of 1919, led by Arthur Eddington. The success of general relativity marked a major milestone in the study of gravity, providing a new framework for understanding the behavior of celestial bodies and the universe as a whole. The development of general relativity also spurred new areas of research, such as cosmology and gravitational physics. Scientists like Subramanian Chandrasekhar and David Finkelstein explored the implications of general relativity for our understanding of black holes, neutron stars, and other extreme astrophysical phenomena. The discovery of gravitational waves by Joseph Weber in the 1960s further confirmed the predictions of general relativity, opening up new avenues for research into the behavior of gravity in strong field environments. Today, the study of gravity remains an active area of research, with scientists continuing to explore the mysteries of gravitational physics and its role in shaping our understanding of the universe. The detection of gravitational waves by the Laser Interferometer. Gravitational Wave Observatory, LIGO, in 2015 marked a major breakthrough in the field, providing new insights into the behavior of black holes and neutron stars. The discovery of gravity has left an indelible mark on the fabric of our knowledge, inspiring generations of scientists, philosophers, and explorers to continue pushing the frontiers of human understanding. Thank you for joining me throughout this historical journey. That's all for today's History with Herodotus. Remember to like, share, and subscribe. And until next time, remember that, to understand the present, we must first understand the past.